Good afternoon, students. In the previous class, you studied electrical current. Now let's go to see electromagnetism. It explains about both electricity and magnetism. So previously, 1820 years before, there were electricity and magnetism are two separate branches, sciences. But after that, after the 1820 years, so because of scientist Oersted, so he discovered the relation between electricity and magnetism. So here the chapter electromagnetism explains very clearly about the relation between the electricity and magnetism. So in this chapter is very most important. So in this chapter, so we will study that is the concepts depending on electricity and magnetism and the devices. Those were invented depending on the relation between electricity and magnetism are dynamo, there is electric working of electric motor, next radio, working of television, radio, etc. etc. So first of all, let us see what is the Oersted experiment. So in the year 1820, the scientist Oersted accidentally, while demonstrating, he discovered that is the deflection of magnetic compass box, the deflection of magnetic needle in a compass box, which was kept under the current carrying wire. So he observed when there is a flow of current to the wire, the deflections of a compass box the deflections of a magnetic needle in a compass box. So magnetic needle deflected due to the flow of current. So actually magnetic needles can deflect only by the magnetic field of magnetism only. But there were no any magnets surrounding it, even though that magnetic needle deflected. So immediately scientist Oersted said, so Eureka, I discovered there is a magnetism by the electricity. There is a magnetism by the electricity. So later, so many scientists carried out the experiments and they invented the different devices which are nowadays those are using a lot. So electrical working of electric motor, dynamo, etc. etc. All these are working depending upon the principle of Oersted. That is, the flow of current produces the magnetic field. Now let's see here what is that Oersted experiment. Now let's see here. So to conduct the Oersted experiment, we have to take a thermocouple. On a thermocouple, we have to make a simple circuit. Okay. So we have to make a simple circuit. Under a wire, if you take a compass box, if a current flows in the circuit to a wire, the magnetic needle deflects. So magnetic needle deflecting means there the flow of current producing the magnetic field, and that the magnetic field exerting the magnetic force on the magnetic needle. So because of that the magnetic needle is deflecting. So this is the Oersted experiment. So this is a very very important. Explain the Oersted experiment. So at that time, how do you explain? You simply write. So take a thermocouple and make a simple circuit. So take a compass box under a wire. Then as long as the current flows through the wire, the magnetic needle deflects. So that concludes that the flow of a current is producing the magnetic field. So this is a Oersted experiment. So this led to the inventions of more devices like dynamo, electric motor, etc., etc. Now in this chapter, so briefly, before going to discuss all, let's go to see about what is magnetic field and magnetic field lines. Magnetic field and magnetic field lines. Okay, so magnetic field, magnets can produce magnetic field lines. So earlier, before 1820 years, people were known magnetism is only by the magnets. But after the 1820 years, people came to know that the magnetism is not only due to the magnets but also due to the flow of currents. The flow of currents can also produce the magnetic field. So now let us see here. Magnets can produce the magnetic field. So this is a Bohr magnet. This is a Bohr magnet. Yes, and here there is a compass box. There is a compass box. Okay, so in this there is a magnetic needle. Over it there are two glass surfaces. Through this surface we can we can see the deflections of a magnetic needle. So in the Oersted experiment, if you take this compass box under a current carrying wire, the magnetic needle deflects. Now let us see here. So here is a Bohr magnet. So when we take the compass box near to a Bohr magnet, we can observe the deflections of a magnetic needle in a compass box. So with this we can conclude that the magnetic needle can deflect by the magnets. So here we should think. So even if the magnet is not in a contact with the magnetic needle, how a magnet exerting the force on a magnetic needle to deflect it? See here, in order to lift a book, in order to hit, we should touch with them. So without touching a book, we can't lift it. So without touching anything, we can't hit to anybody. But here, a magnet is deflecting the magnetic needle in a compass box, even if a Bohr magnet is not in a contact with the compass box. So how it is possible means, so about this you have studied in your 9th class. Okay, so for the force field, there is a field force at a distance, field force. Okay, so let's see here how this magnet is exerting the magnetic force on a magnetic needle, even if the magnet is not in touch with a compass box, means around the magnet, its effect exists in a three-dimensional space, and that is called as a magnetic field. When we take this compass box in the field of a magnet, then the magnetic needle in a compass box experience the magnetic force. Because of that magnetic force, this magnetic needle deflects. So this is the example for force at a distance or as a field. Already you have studied in your 9th class about a gravitational field, magnetic field, etc., etc. Even if the two bodies are not in a contact, one body can influence the another body. At the same time, the other body can influence the one body. So how it possible means? Because of a gravitational field. If one body enters into the field of another body, then it experiences the gravitational force of one body. That is due to the gravitational field. So through the field, it exerts the gravitational force. So in the same way, magnets can exert the magnetic force on the magnetic materials through their field. Magnetic field exists around the magnet in a three-dimensional space. Now let's see here how magnetic field lies around a magnet. How magnetic field of a magnet lies around a magnet. Suppose, let's take here, this is a ball magnet, this is a ball magnet, this is a ball magnet. So before going to that, let's see here, this is a compass box. We can use this compass box as a directionality. In a compass box also, there is a magnet, but there is a small magnetic needle. We use this as a directionality because it shows the directions of north and south. So always a freely suspended magnet shows north pole of the earth and the south pole of the earth. North pole of the earth and the south pole of the earth. Now see here. So here is a magnet. So I am here. It is suspending freely by means of a thread. Now see here. So it is aligning in the direction from south to north. So even if I try to twist it, but it aligns from south to north direction. From south to north direction. Now let's see here why a freely suspended magnet at any way always aligns in the south and north directions. In the south and north directions. Because what is the influence? What's the influence is there on this magnet for aligning from south to north of the earth? So let's see here why the freely suspended magnet and the magnet needle in a compass box always shows from south pole of the earth to north pole of the earth means earth is a big magnet. The earth is rotating around itself and is also rotating around the sun. So due to the rotation of earth, the modern state of iron, nickel, etc. Okay, so this also moves and this can produce the current and this current can produce the magnetic field. So there is a reason to say for the magnetic field of earth. Okay, later we will see that. So earth is a big magnet. If it is a magnet, it produces the magnetic field that is called as Earth's magnetic field. The Earth's magnetic field lies from south pole of the earth to north pole of the earth. The direction of resultant magnetic field of earth is from the south pole of a magnet to north pole of a magnet, or from north pole of a magnet to south pole of a magnet. So that's why here this magnet, any magnet settle or else lies in the direction of resultant external magnetic field. Any magnet aligns in the direction of resultant external magnetic field. Here also, why this magnet is aligning from south pole of the earth to north pole of the earth means, so here the magnet is aligning in the direction of magnetic field of earth. What is the direction of magnetic field of earth means? That is from south pole of from north pole of the earth to south pole of the earth. So here it is the freely suspended magnet. Okay, so one end of the magnet is showing the one pole of the earth, the other end of the magnet is showing the another pole of the earth. And here, so we take the end of the magnet which shows the north pole of the earth is called as a north pole of a magnet, and the end of a magnet which shows south pole of the earth is taken as a south pole of a magnet. Actually, the geographical north pole of the earth behaves as is actually south pole of earth magnet. The geographic south pole of earth is actually a north pole of earth magnet, and we know that. So north pole, south pole, south pole. That is, like poles repel each other, and unlike poles attract each other. Unlike poles attract each other. So that's why a magnet can settle or align in the direction of a resultant external magnetic field. That's why here a magnet aligns from south to north of the earth, because the earth's resultant magnetic field lies from south to north of the earth. Now let's see here. So we draw the directions So here these are the conventional directions. This is west to east, and this is south to north. South pole of the earth, north pole of the earth, west and east. And the freely suspended magnet, the end of the magnet which shows the north pole of the earth is taken as north pole of a magnet, and the end of the magnet which shows the south pole of the earth is taken as south pole of the magnet. Now, if we take a compass box, near a magnet, that the needle in the compass box deflects. The needle in a compass box deflects. Okay. So why here the needle in the compass box deflecting means the magnetic needle in a compass box always shows the resultant direction of external magnetic field. Here what is the external magnetic field? Here the external magnetic field is magnetic field due to a Bohr magnet. So here there is a magnetic field due to earth also, but the magnetic field due to earth is very small. It is in terms of 10 to the power of minus 5 Tesla. We can neglect it. Or else, otherwise, if we don't neglect that, let's take it is here there is a resultant magnetic field, and that resultant magnetic field is due to the magnetic field of a magnet and due to the magnetic field of earth. And here this magnetic needle showing the direction of resultant magnetic field of magnet and earth. Okay, if you take the magnet at a different positions, then the magnetic needle in the compass box shows the different directions, which means the magnetic field due to a Bohr magnet is not in the same direction at all the places around a magnet. The magnetic field lies in a different direction. Okay, so this shows the magnetic field due to a Bohr magnet lies in a different directions. Now, so here you take a compass box. Okay, the magnet needle shows one direction, and here you put one dot. So further you remove the compass box from there and take the compass box here. Here arrow here magnetic needle shows one direction. So here you put one arrow mark, and next similarly you take away this compass box from here and take it here. Here it shows one arrow mark. So like that, you put the dots at the points shown by the arrow mark. Later, you join all those dots, and this is called as the magnetic field line. And now take a compass box at another point and at another point at the north pole, and again the magnetic needle shows the different directions at different points. At those points, you put the dots, and later you join all those points. So these are the magnetic field lines. So in this direction, in this way, in this also you do the same. So you get the magnetic field lines shape. So in this way, okay. So these are the magnetic field lines around a magnet. So here the direction of magnetic field lines from north pole of a magnet to south pole of a magnet. So these are this is the shape of magnetic field lines lies around a magnet. So the magnetic field not only lies, okay, beside a magnet, okay, the magnetic, if you take the compass box over a magnet, there also magnetic needle deflects. Means what? There is a magnetic field in a three-dimensional shape, around a magnet. Magnetic field due to a ball magnet lies in a three-dimensional shape around it. Now, so what is the direction of a magnetic field due to a ball magnet? So to know the direction of a magnetic field, okay, so by taking the magnet here, and here we take a compass box, okay. In a compass box, the magnetic needle shows one direction, and that the direction is the direction of a magnetic field at that point, okay. So how this direction drawn? This direction drawn is like a tangent to the magnetic field line. That means the direction of a magnetic field at any point lies along the tangent drawn at that point to the magnetic field line. The magnetic field direction lies along the tangent drawn to the magnetic field line at any point. Suppose if you want to know the magnetic field direction at this point, so here you have to take compass box, then the needle shows a direction. Now in that direction you draw a line. See, this line is like a tangent to this magnetic field line. That means the direction of a magnetic field is along the tangent to the magnetic field line at any point. That means at any point the direction of magnetic field is along the tangent drawn at that point to the magnetic field line. So in this way we can know the direction of magnetic field due to a ball magnet. If we observe the direction of magnetic field lines, the direction of magnetic field at different points are different. That means the magnetic field direction is not the same at all the points around a magnet. The magnetic field direction is different. And now let us see here about the strength of the magnetic field. Okay. Now let's see here how do we know the strength of the magnetic field means. So around a ball magnet, if we observe, okay, there are some regions, okay, at the ends of a ball magnet, the magnetic field lines are very close, whereas beside the middle of the magnet and middle of the magnet, the magnetic field lines are separated by large distance. That means where the region where the magnetic field lines are closer, there the strength of the magnetic field is more. And the region where the magnetic field lines are separated by large distance, there the strength of the magnetic field is less. Now see here, Here the magnetic field due to a ball magnet is called as a non-uniform magnetic field. So why it is called as a non-uniform magnetic field means because here the strength and the direction of a magnetic field is different at different points. If the magnetic field direction is different from point to point and its strength also changes, means that is called as a non-uniform magnetic field. In both the strength and the direction, if any one of the direction or strength of the magnetic field changes from point to point, then we call as that is called as a non-uniform magnetic field. So here that is the ball magnet gives the non-uniform magnetic field. Non-uniform magnetic field. Now let us see here about the characteristics of a magnetic field lines. Characteristics of a magnetic field lines. See here the magnetic field lines. Here the magnetic field lines. It seems the magnetic field lines are coming out from the north pole of a magnet, and seems the magnetic field lines are entering into the south pole of a magnet. That means the magnetic field lines come out from the north pole of a magnet and enters into the south pole of a magnet. That means the magnetic field lines are closed curves. The magnetic field lines are closed curves from north pole to south pole. See, outside a magnet, the direction of magnetic field lines is from north pole to south pole, whereas inside the magnetic field lines are from south pole to north pole. South pole to north pole. Okay? The magnetic field lines outside a magnet are from north to south, whereas inside a magnet are from south to north. That means magnetic field lines are closed curves. We don't say where actually magnetic field lines start and where actually magnetic field lines end. So magnetic field lines do not start at any point, do not end at any point. Magnetic field lines are closed curves. Magnetic field lines, the direction of magnetic field lines outside a magnet are from north pole of a magnet to south pole of a magnet. Inside a magnet are from south pole of a magnet to north pole of a magnet. Now see here the another characteristic of magnetic field lines. See here, no two magnetic field lines intersected at anywhere here. Okay, no two magnetic field lines intersect. No two magnetic field lines. No two magnetic field lines. No two magnetic field lines intersect at anywhere. At anywhere. Okay, why two magnetic field lines do not intersect at anywhere? What happens if they intersect? Now let's see here. Suppose if we assume at anywhere two magnetic field lines are intersected. Okay, at any point two magnetic field lines are intersected. Now at the intersecting point, to know the direction, we should draw the tangent. Now let's draw the tangent to this magnetic field line. If we draw the tangent to this magnetic field line, its direction is in this way. And if we draw the tangent to this magnetic field line at this point, in this way. Okay. So here at a single point we got two directions. Okay. But at a single point having magnetic field two directions is highly impossible. That's why no two magnetic field lines intersect at any point. So this is about information about magnetic field and magnetic field lines. And moreover, this is a bore magnet, so it will have two ends. So one end is called as a north pole and another end is called as a south pole. And here monopoles do not exist. Monopoles of a magnet do not exist. Okay, so in a magnet always there are two poles north and the south pole. In order to divide the poles of a magnet, if we cut a magnet into number of pieces, then each piece of a magnet further again behaves as a singular magnet. So that's why no two magnetic field lines, because there are no open curves of magnetic field lines, there are the closed curves of magnetic field lines. So that's why always there are two poles of a magnet. So poles of monopoles of a magnet do not exist. So further, yes, like poles of two magnets repel each other, and unlike poles of two magnets attract each other. So this is the few information about Oersted experiment and magnetic field and magnetic field lines, and about the strength of the magnetic field. Okay.